In the last video, we were taking a look at Faraday's law of induction. And now here I'd like to transition into thinking about an electrical device that is called an inductor. So we're going to make a circuit that involves one. So we'll have a battery, we'll have a resistor. If you put an arrow through a symbol, that means that's variable. So this means there's some way to turn a knob and change its value. And now here, whoops. And now here, we're going to have our inductor. So notice here, I drew the, whoops. Let's try that one more time. So here, notice I drew the symbol as a bunch of loops rather than jaggies. This is because what an inductor is typically a coil of wire. Often it's wound around a core of iron because the magnetization of the iron helps to enhance the effect. But you could just plain wind it around, say, just something to give it some shape and let it have an air core. And so for our purposes, we'll just think about an air core inductor. If there was an iron core to it, they would draw a couple of lines off to the side to remind you of the iron core. All right, so what I'm going to do is I'm going to imagine here that initially we've got a pretty decent resistance here. And what I'm going to ask you what's going to happen to the current through the circuit. We know that since this is the positive terminal of the battery, that's the negative, that the current through the circuit is doing something like this. But wondering what will happen to the magnitude of the current through the circuit as I decrease the resistance. So pause the video and get back with me on that. So yeah, twinkle, as you'd expect, if I decrease the resistance, the current does indeed go up. So that's our first little checkpoint. If the resistance goes down, the current is going to go up. All right. So if the current is going up, what does that mean for the magnetic flux through the inductor? Okay, yeah, reasonably enough. If the current goes up, this means we're making a bigger magnetic field inside our coil of wire, because that's what an inductor is a coil. So the field goes up, the area doesn't change, so the magnetic flux increases. Alrighty, so we've got ourselves a coil of wire and we have an increasing magnetic flux. We have a time varying magnetic flux here. Does that mean we induce an EMF? The answer is actually, yes, we do. We induce an EMF. The magnetic field still just, the time varying magnetic field sets up an electric field that's a whole bunch of circles around the inductor. Though the electric field will be shoving charges around, doing non-conservative work. So sure enough, we induce an EMF. Now, I am going to assert here that the polarity of our EMF is such as to oppose the change in the current through the circuit. I mean, it could be that way or it could be the other way, right? I'm asserting that it's this way. So why is that? I can think of at least a couple of different ways to argue this. Go ahead and pause the video and see what you come up with. Okay, so the two arguments that I can think of are, if it weren't this way, so say it were the other way, where it would be supporting the change in the current, then once again you've created a perpetual motion machine of the first kind. This would be basically acting like a battery with the same polarity as this battery. And as the current increases, that would increase the magnetic flux, and we would just keep on going and going. And so we would have created a perpetual motion machine of the first kind. We could just boil a whole bunch of water off of the resistor or whatever and do all the work that we would ever want. And the other way to think about it is that it is a consequence of Faraday's law of induction. Because keep in mind here, if the current through the inductor is going up, that means the magnetic field strength is going up. So we have an increasing flux. That means that the induced field would have to oppose it, which means that we must be inducing an EMF to try to oppose the change in the current. So this sort of phenomenon gets known as a back EMF. And inductors aren't the only place you see it. You also see it in electric motors. Because if you think about it, an electric motor is also its own generator. As you increase the RPM of the electric motor, what's happening? You are inducing, you're having a greater and greater change in magnetic flux going through the coil that induces an EMF. So as a result, the amount of current that the motor can pull actually decreases as RPMs go up. This is why if you have a seized motor and you're trying to drive a current through it, the resistance is quite low and you can actually burn up the motor from all the heat generated from the basically short circuit you're creating. On the other hand, as the RPMs go up, the back EMF increases. This is opposing the EMF being supplied by the battery, which means you're decreasing the current through the motor, but that means it actually becomes a less effective motor in the sense that it can provide less torque. So this explains why it is that electric cars can smoke straight off of the stoplight virtually any car that isn't built to be a flat-out racing car in a professional racing series. And this is because they produce maximum torque at 0 RPM because there's no back EMF. As the RPMs go up, the EMF increases and the available torque that the motor can provides decreases. All right. Now, while that's all very interesting, sometimes we actually intentionally use inductors as electric devices, and so we want to go ahead and start to characterize those. So we'll define the inductance here. And I have no idea why the symbol for inductance is L. I am just going to guess that we have run out of letters. We're going to define it as what's called the flux linkage over the current. So keep in mind here, an inductor is just a giant loop of wire. And as we run a current through it, we are going to have a magnetic field going through it. Now, the business with the induced EMF, we already saw from Faraday's law of induction, is it's going to depend on the number of turns and on the magnetic flux going through each coil. So that seems pretty natural. And this magnetic field strength is itself proportional to the current going through, so it makes sense that we are saying per unit current. All right. So we can go with Faraday's law of induction here. And now that we've worked out that the EMF has to be a back EMF, we can write that the EMF is equal to minus N d phi b dt. And so this is because this is opposing this. The induced EMF is attempting to shove charges around to create a magnetic field that opposes the change in the magnetic flux going through here. All right. So the voltage across our inductor, delta V sub L, will be equal to this EMF. So this will be minus, well, this, but I'm going to bring the N inside the derivative. I'm allowed to do that. It's a constant. But now, from our definition of inductance, if I times both sides by L, I can observe that that will be minus d dt of Li. Now, the idea with the inductance here is that this depends purely on the details of the shape of this. The magnetic fields, the flux linkage depend on the number of turns. That's a detail of construction. The flux will depend on the area and the magnetic field strength. The magnetic field strength will depend on the shape of how these coils are turned and on the current. So if we divide the current out, everything else depends on the details of construction. So this will be a constant. So times both sides through by L, I will get that it is minus ddt of Li, but the inductance, we just argued, only depends on the details of construction. So we can say that the voltage across our inductor is minus L di dt. So with this minus sign here, if the current through the inductor is going up, it means the magnetic flux goes up. We're trying to oppose that change. So the EMF we induce would oppose that, thus the minus sign, and we would have a voltage drop across the inductor. If the current were decreasing, it would be the same kind of deal here. Di dt would be negative. The magnetic flux would be decreasing. We would be seeking to oppose that change. So a negative of a negative would be positive, mean that the voltage across the inductor would be in the same polarity as the battery in the circuit. So we'd be attempting to reinforce the collapsing magnetic field. Now the units of inductance here are the Henry. And 1 Henry is a volt second per amp. Or since we know that a volt per amp is an ohm, we can also write this as ohm seconds. Now, inductors will show up more when we look at AC devices, but one application, there's a couple applications that they do have in DC. One of them that we can use is if we want to ramp a circuit in. If an inductor is initially de-energized, there's no magnetic field built up in it, and there's no current passing through it, if you flick the switch, your current jumps from nothing to something in a hurry. Well, that's going to try to create a huge time rate of change of magnetic flux through the inductor. So you'll wind up getting a substantially large back EMF. So this will have the effect of damping down the increase in current. So instead of it being nearly instant, which might cause damage to devices or something like that, it will indeed ramp up a little more slowly. Now, as a little tidbit here, you will notice that as the current flows through the inductor, and it's interacting with its magnetic field, there will be a magnetic force. And if you play with the right hand rule, you can convince yourself that this is going to try to collapse it down a little bit. There will be some twisting action happening. This is why light bulbs, for instance, have a bit of are coiled up. It's to help absorb some of the shock in that twist. Alrighty. Now the other benchmark that we have is once the circuit's been going for a long time, now we've built up our magnetic field and it isn't changing anymore. So at that point, it acts like a wire. So sort of the benchmarks here we have is basically like when the switch is just closed, the inductor acts like a break in the circuit. And after a long time, it just acts like a wire. This is the exact opposite behavior that we saw for capacitors. Now, inductors will also get used to do things like, say, store energy in a magnetic field, and then by suddenly opening the circuit, you can do things like jump a spark. That's what the coil in a car is used for, to cause a spark to jump in a spark plug. So let's just take a quick look at some circuit here. Let's say we have a 3.2 millihenry inductor, and the current going through the inductor as a function of time looks something like this. From 0 to 2 seconds, we ramp up from 0 amps up to 4. Then we'll say from 2 to 5 seconds, it stays constant at 4 amps. And then from 5 to 9 seconds, it falls back off to 0. Let's go ahead and make the corresponding graph for the induced EMF across the inductor, or the voltage across the inductor. So from this, we remember that the voltage across the inductor will be minus L di dt. Now these are straight line segments, so di dt in each case will just be equal to the slope. So here we have a rise of 4 volts over a run of 2 seconds. 4 amps over 2 seconds. So this will be 2 amps per second here. Here this is flat, so the slope is 0 amps per second. And then finally here, the slope is minus, because it's going down, 4 amps over 4 seconds, so minus 1 amp per second. So armed with that and the fact that we have a 3.2 millihenry inductor, we can calculate the voltage across the inductor for each of these time periods. So delta V will be equal to we'll just say 3.2 millihenries. times 2 amps per second. Now a Henry times an amp per second is a volt. And then we still have the milli prefix left. So this will be, minus L di dt. So this will be minus 6.4 millivolts. In this segment, delta VL will be 0 because the current isn't changing. Then finally here, delta VL will be minus 3.2 millihenries times minus 1 amp per second. So minus and minus cancels. We're left with plus 3.2 millivolts. Alrighty, so we can go ahead and plot that. So voltage across the inductor in volts, time in seconds. Our intervals again were 0 to 2, 2 to 5, and 5 to 9. So this will be minus 6.4, so this is in millivolts. We'll say minus 3.2, because I'm lazy, 3.2 plus 6.4 here. So our graph is going to look something like that. Cool. So to give some flavor for how the geometry of inductors affects the inductance, let's find the inductance of a solenoid. So you remember from earlier, we said that the magnetic field strength of a solenoid was equal to mu naught times the number of turns per unit length. So this will be the number of turns of the solenoid over the length. That's probably the easiest way to think of it, times the current. So this means that the magnetic flux would be B times the area. So we just times that by an area. And we will want the flux linkage to go into inductance. So the flux linkage is just going to give me timesing through by an N everywhere. By the way, I'm not aware of a symbol for flux linkage. Any writing I've ever seen will just say the flux linkage, comma, NV, comma. Probably in some specialty text somewhere there is a symbol for it. I'm just not aware of one. And then we remember that the inductance is the flux linkage over the current. So if I divide the current back out here, I'm left with mu naught N squared over L times A. So it just goes as the square of the number of turns, inversely as the length, and directly as the area of the loop. So I'm going to finish off with one last thought here, and that is that I will argue that all circuits that you wire have a self-inductance. Why is that? Pause the video and get back with me. Okay, it's because every circuit, and it's literally in the name, circuit, is a current carrying loop. So it's a single churn, every circuit is a single churn loop, which means that every circuit is a very crappy inductor. Now, most of the time this doesn't matter, but sometimes when you're doing fussy design, it does.